Hello and welcome back to my Physics Online video lecture supplement series. In today's video, I'm going to continue my second set of lectures for the second semester's worth of Introductory Physics. And this is again the lecture covering electric forces and electric fields. And in today's video, we're going to look at the third part of this lecture set, which is Gauss's Law. And so here actually is a portrait of Mr. Gauss himself. The basic idea behind this law is as follows. We've studied so far Coulomb's law, in which we can basically calculate the actual electric force that is between two charged particles, the electrostatic force that two charged particles exert on one another. And we saw that it has a form very similar to Newton's law of universal gravitation. Then we discussed that both electric forces and gravity itself are what are called field forces. So they can act at some distance. So the two particles are not in contact with each other, in other words. And that was in the first part of this set of lectures. So then in the second part, we discussed the idea of field forces and field lines, and specifically the electric field and electric field lines. So that is Michael Faraday's contribution to this field, or one of his contributions to this field. So the electric field lines give us a very convenient way of basically visualizing what the electric force might be at a point given a charge. It basically sort of a way of visualizing the influence via the electrostatic force that a given charged particle or charge configuration might have on the region surrounding it. So in today's lecture, what we're looking at is an application of the electric field, which is in Gauss's law. And basically what this does is it allows us in some cases to more easily determine the actual electric force that is going to act on an object than Coulomb's law would have allowed. In other words, it lets us more easily and conveniently calculate the electric field strength at a given location in space, given some charge configuration. So how do we do that? Well, in order to actually calculate the electric field strength at a location in space, we have to understand a new concept called flux. So what's flux? Flux is a measure of how much a field in general passes through or penetrates through a given surface. So since we're talking about electric field lines, the electric field flux, which I may revert to just calling flux in this video, is basically how much the electric field vectors pass through or penetrate through a given surface. So the only part of the flux that actually counts, of the field that actually counts, that is the part that is perpendicular to the surface itself. So this means if there's some angle between the electric field line locally and the surface, then that angle also gets taken into account. And the field line, which is tangent to the surface, is going to provide a flux of 0. The field line which is perpendicular to the surface is going to provide a flux of whatever the field strength is, E, times whatever the area of the surface is through which this E is fluxing. So we use this capital phi, or capital phi, to represent flux, and so phi sub E is the electric field flux, and the simplest calculation of it is a uniform electric field passing through a flat surface, in which case we can simply use E dot A, which means that ultimately we take the component of the electric field which is perpendicular to the surface and we multiply it by the area of the surface. Now this may seem counterintuitive to you, because if you've been paying attention to the dot products that we've done so far, usually when you dot two things with each other, let's say vector x and vector y, you calculate the dot product by taking the magnitude, that is essentially the length of x, the strength of x if it's a field, and you multiply it by the magnitude of y, and then you multiply it by the cosine of the angle between x and y. So usually when we talk about dot products, we're referring to two vectors and trying to figure out what's the projection of one vector onto the other vector. In other words, what components of the two vectors are commonly parallel to each other. So the more parallel two vectors are, the larger will be their dot product. But here we're saying that we want the perpendicular component of E to A, and yet it's a dot product. So what gives? Well, it turns out that when trying to find the area of a surface, you can basically specify a given surface in one of two ways. When I say a surface, again, I'm meaning, in the simplest case, a flat surface. So a flat surface basically would represent something like a plane or a slice of a plane. So how is it that you can specify a plane? Well, one way to do it is to specify two vectors which are in the plane. So maybe I specify the vector x and I specify the vector y. So by specifying the xy plane, I have now denoted a specific plane within my coordinate system. The other way that I could go about doing this, and note that I need not have two vectors which are perpendicular. I might have specified another vector like this, that's say the y prime vector or some such thing. It just has to be two vectors which are not parallel and which are in the plane. So that's one way of specifying a plane. The other option is, if I want to specify that same plane and I want to use only one vector, then I can use the vector which is perpendicular to that plane, which is in this case the z vector or the z-axis. So by saying I mean the plane that is perpendicular to z, I have also specified the direction of the plane. So when discussing the area vector of an object, so here's my object, I could specify two dimensions within this vector, or within this plane. So for example, when we have a rectangle, usually we specify the area by figuring out what is the length x, figuring out what is the height or width y, and then we multiply the two together and we say that's the area. Well, there we've calculated a scalar. If I want to multiply x times y and find the actual area of this, and x and y are vectors, what can I do? Well, let's say I take a dot product between x and y. If x and y are perpendicular to each other, then this dot product is going to be 0. So the other option is to take what's called a cross product. So x cross y is not going to be 0 if x and y are perpendicular. In fact, it will only be 0 if x and y are parallel, or if one of these two vectors has a magnitude of 0 to begin with. So in fact, if you think about taking a rectangle or a square and trying to find the area of it, if I was to give you two random dimensions, let's say I give you the base and maybe I give you the diagonal, so x times r. There's some angle theta between these two. If I want to find the area of this, I could multiply by x times r times the sine of angle theta. And what's the angle theta give me? It gives me, in this case, y. You can see that y is r sine theta. Well, this process right here is the same thing as taking the magnitude of the vector that we get by doing x cross r. So in fact, it's the cross product, or at least the magnitude of the cross product, which generally speaking is going to give us the area of a rectangle. Now coming back up here, what happens if I take x cross y? Supposing that we have x cross y, what we should end up getting is a vector that is perpendicular to both x and to y. So what vector would that be? Well, it would be the z vector. So in this case, if I want to find the area actually is usually given by something like x cross y or x cross r. So that means that this area vector needs to be perpendicular to both x and y. In other words, it's perpendicular to the two vectors which are in the plane, and thus by extension to all vectors which are within the plane. Alright, so hence the flux, we're taking E dot A. A is actually perpendicular to the surface. So therefore, this is equivalent to calculating the component of the E field which is perpendicular to the surface times the area of the surface. So that's where this equation is coming from. The units we can get by looking at what the units of each of these two terms are. E has units of newtons per coulomb, because if you multiply E times Q, in other words, if you multiply electric field strength times charge, you get the force that's being applied to that charge by that electric field. So E is newtons per coulomb. A, of course, is meters squared. So our units are newton meters squared per coulomb. And one last little note on this page is that if we want to figure out what the relative electric field strength is, it's always going to be proportional, and this is relative strength of the flux of the electric field, I should say, through two given surfaces. It is going to be relative to the number n of the E field lines, the electric field lines, which passes through each surface. So if you have two different surfaces and you get the same number of field lines passing through each surface, regardless of the angle that it makes between the two, as long as it actually does pass through and not run tangent to. If you get the same number of fields passing through each, then it means that the flux is the same, or the magnitude of the flux is equal for those two surfaces. If you have one that has twice as many field lines passing through it as the other, then the flux should be twice as great through the surface with twice as many field lines. So let's talk about a couple conventions that go with calculating flux. First of all, I've already talked a little bit about using the vector which is perpendicular to a surface at each point of the surface to represent the area. So that part's kind of covered. This additional definition is because the surface may or may not actually be flat. So you may have a changing area vector as you go around the surface. And second of all, what this means is that we can calculate the flux by taking E times A times cosine of theta, where theta is the angle between the area vector and the electric field vector. Okay, so here's the more familiar form of a dot product. E dot A should be E A cosine theta. So now we have made each of our sort of self-coherent definitions become coherent with each other. Okay, the next thing is that if you have an electric field line that is passing through a closed surface and the field line is entering into the surface, then we take that flux of that field line to be negative. If it is exiting through some face of the surface, then that field line has a flux which is positive, or the field locally has a positive flux. So in this picture right here, this is not an entirely closed surface, but suppose we put, a base and then maybe a couple sides to make it into a closed surface, like a prism. You can see that the field lines back here are going into this prism through this face, so they have a negative flux on this face, and then they're coming out of this face, which would mean that they'd have a positive flux through this face if this were a closed surface. Alright, so let's look at a couple simple examples before we move on and sort of add to our definitions for electric flux. For our first example, we have an electric field of known strength, and we're passing through a flat planar surface of known area, and then there's some angle between the field and the area vector. So we're going to calculate the flux out of this plane. So let's draw a simple cartoon of this. The plane maybe has an area vector like this. The electric field is 60 degrees off from the perpendicular, so this right here is the direction of the electric field. There's a 60-degree angle right here. The area vector has a magnitude of 40.0 meters squared, and the direction we can call A hat just to represent our direction. The electric field has in turn a strength of 30.0 Newton per Coulomb, and maybe a direction of E hat just to give it some direction. So if we want to calculate the flux out of this thing, we use flux equals E dot A, which is going to be E A cosine theta. So we have 30 newtons per coulomb times 40.0 meters squared times cosine of theta. In this case, we are using cosine of 60 degrees, which is a half. So it's this times half. So this is 40 meters squared, not 40 meters quantity squared. So if we do multiply all these things together, we have half times 40 is 20, times another 30 would be 600. So the total flux looks like it's going to be 600 Newton meters squared per coulomb. So there, now we've calculated the flux out of this plane. For our second example, we have a charge of magnitude 0.1 millicoulombs. So we'll go ahead and put that right here. Plus 1.00 millicoulombs is the charge. And it's in the center of a hollow, neutrally charged conducting sphere. So our sphere maybe is out here. And something like this maybe. And the radius was 0.1 meter. R equals 0.1 meter. So now we've got to get the flux out of here. So as you know from Coulomb's law, the electric field strength should be such that the test charge placed out here, Q test, times the electric field should give you the force. So this is basically force over Q test, and so that would be Coulomb's constant times Q test over R squared times Q test. So we can eliminate those two things. And the area of a sphere, how do you get the area of a sphere? Well, you do area is equal to 4 times pi times R squared. So this is what the area will be. Now we need to know, are these two vectors parallel, perpendicular? What's going on there? Well, the electric field lines should radiate outward, so they're moving out radially from this point. And so review the last set of notes if you've forgotten how to draw the electric field lines for this. Basically, they're going to be radially oriented like so. And so if they are radially oriented, that means that everywhere that they're hitting the surface of this sphere, they are in fact perpendicular to the surface, which means parallel to the area vector. So we can in fact write that the flux is E dot A, which ends up just being E times A, and so that's KE times Q over R squared times 4 pi R squared. So the r squareds cancel, and what we're left with is that the flux out of this sphere is KEQ times 4 pi. So that is 8.98 times 10 to the ninth Newton meters squared per Coulomb squared, times this thing was 0.1 millicoulomb. So that's 1 times 10 to the minus 3 coulombs. And then we can multiply that by 4 pi. So we should be able to multiply all these guys together and get out the flux out of the sphere. So the answer to that is approximately, seems as we only had one significant figure up here to work with. It's going to basically be approximately 1 times 10 to the 8th Newton meters squared per Coulomb. And if we had more significant figures to work with, this could have more significant figures. For example, if this was 0.100, we would have had 1.13 times 10 to the 8th. So, okay, we've calculated the flux out of that sphere. And before moving on to the next example, I want to note that we can now quickly, for this amount of charge, calculate the flux out of all spheres upon which this charge is centered. Or in other words, all spheres which are centered upon this charge. Because they will all, in fact, have the same answer for this given charge at the center of the sphere. Because you'll notice that the r squared terms dropped out. That means that the radius of the sphere doesn't matter for flux's sake. So, therefore, a sphere that had a 1 meter radius would also have the same flux of 1 times 10 to the 8th Newton meters squared per Coulomb. So, you can now very easily calculate the flux out of any sphere. Because if we up this number, if we change this number to, say, 2 millicoulombs, well, double this. If we change it to 8 coulombs, then multiply by 8,000 here, and so on. So now you can easily calculate the flux out of any sphere for any point charge placed at the middle. With that said, what would have happened if this charge had been negative? For example, negative 1.00 millicoulomb. What would the difference be? So if we change from plus to minus, here's our sphere. Here's the point at the middle of the sphere. It's kind of a bad drawing. Well, then the electric field line configuration might look more like this, as best as I can free draw this thing while not looking where I'm drawing. And all the arrows point inward instead of outward, because it's now a negative charge. And nothing else changes. So that means that if the charge is negative instead of positive, and you're asked, what's the flux? Then you can reply, it's negative 1 times 10 to the 8 Newton meters squared per Coulomb. Okay, so now that we've looked at the simple case of, for example, the flux through a flat plane or surface, or the flux through a sphere in which the field is everywhere perpendicular to, or at least everywhere the same direction relative to the surface that it's fluxing through, we can flux some more sophisticated physics muscles by basically considering what happens if the field lines are not in the same direction at each point relative to the surface. So what do we do in that case? Well, if the field lines are broad, or if the surface has a very gradual amount of change to it, etc., we might try doing something like figuring out what the flux is for a segment of the surface, and then adding up all the fluxes together, and that gets us the total flux through the whole surface. And that works out very nicely if you have a surface which is not totally regular, but it maybe changes by small amounts. For example, maybe you have a field which is everywhere in the x direction or horizontal direction, and you have a surface which makes like a triangle shape. So then you'd find the flux through the top part, you might find the flux through the next side, and the flux through the last side, and then you're done. This would look something like this, if I can just use a simple drawing. Quick rhetorical quiz for you. Can you figure out what the total flux is through this surface? And second of all, can you figure out, based on just this sketch, which face of this surface has the greatest flux through it? Or maybe I should say greatest magnitude of flux, since this face is negative and these faces are positive. Which one has the least flux through it? So there's a quick rhetorical quiz for you. In any case, if this one is face number 1, this one's face 2, 3 is over here, 4 is here, and then 5 is sort of across from 4, you could get the total flux through the entire thing by adding the flux through each individual face together. Like so, flux of E through 1 plus flux of E through 2 plus flux of E through 3, and then 4, and last of all 5. So this would get you the total flux through this surface, and more about that shortly. In any case, you basically would take each one of these faces, which has a uniform flux through the face, and you basically take E dot A for each face, and that's the flux through that face, and you'd add them together. And you'll note that some of these faces have positive and some of these faces have negative. So in answer to the rhetorical quiz, you can see that there's an equal number of these lines going into the surface as there are coming out, so the net flux in this case should actually be 0. As for which face has the greatest magnitude of flux, this one is the one with the greatest magnitude. These two are 0 each, so they have the least magnitude. And you can see that because the field lines are actually parallel to both surfaces 4 and 5, so there can be no flux. And once you've eliminated those two, you can see that the most number of these lines actually pass through face 3, and an equal number pass through going into as pass out going out of 2 plus 1, hence 0 total. Okay, but that's a fairly simplistic case in some ways. The original drawing that I showed when discussing this more general case didn't show something that could easily be broken up into, for example, 5 rectangular components through which the flux is uniformly passing. In other words, a uniform direction. Oftentimes you end up with something like this that is maybe a curve, and so we have to go one step beyond just adding each of the individual faces together, and that is to take very small sections of this surface, that's in other words a small area dA, and then find what the flux is through that local unit dA, and then to get the total flux you integrate E dot dA. Now this right here is not a closed surface, it's sort of showing an open surface. Very oftentimes, and specifically when using Gauss's law, you have a closed surface. And if you have a closed surface, we can re-express this integral as this funny looking integral that has a little circle through it. What this basically, the symbol means that we're taking the integral over the entire area of a closed surface. And so Gauss's law is going to hinge upon using an entire closed surface and taking the area through all of it. So what is Gauss's law? Well, Gauss's law actually is very simply expressed. This is it. Gauss's law in its simplest form says that the total electric field flux through a closed surface, any closed surface, is equal to the total charge enclosed divided by the permittivity of free space. And recall that we actually saw this permittivity of free space in part 1 of this lecture set. It is basically 1 over 4 pi times k sub e. And it has an actual value 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. So actually these units are the reciprocal of the units for Ke because it is equal to some constant, 1 over 4 pi, times the reciprocal of Ke. And Gauss's law works nicely because it can be constructed using any arbitrary surface provided that that surface is in fact a closed surface. And it's worth noting here that the Gaussian surface itself is actually a fictitious surface. It's something we use to make the calculation easier for ourselves. It is not a surface that necessarily exists somewhere in space. It's sort of like a hypothetical construct, hence a fictitious surface. And we often call these surfaces a Gaussian surface or Gaussian surfaces. So let's look at a couple consequences of this. The first of them is that if you have a field which originates externally and which basically terminates externally, then the total flux through the surface will be 0. Why did I say and terminates externally? Well, recall the rule for electric field lines is that they have to originate on a positive charge and terminate on a negative charge. If you don't have any positive or negative charges nearby, then the field either is originating at infinity or it's terminating at infinity. So if there are no charges enclosed inside of the surface in question, the Gaussian surface, what that means is that the field lines can neither originate nor terminate inside the field. And so for every field line that goes in, there is also a field line that must come back out, hence a net flux of 0. Again, that is because if a field line goes into a surface, it has a negative flux through that surface. If it goes out of the surface, it has a positive flux through that surface. So again, same number going in as coming out is equivalent to saying you have negative so much flux, you have positive the same amount of flux, you add them together, you get 0. So this diagram actually shows the 3 basic possibilities by taking 3 slices off of this oblong spheroid. And basically your 3 possible choices are you have the electric field passing into the surface, in which case theta is going to be greater than 90 degrees but less than 180 degrees, and so cosine of theta is going to have a negative value, hence you get a negative flux inward. Your second possibility here is that the field is locally parallel to the surface, in which case the angle between the two is 90 degrees and so the flux is 0. And the third possibility is that this is coming out of the surface, as here. And so this angle is less than 90 degrees and, of course, greater than 0 degrees. And as a result, cosine of the angle is a positive value, and so you end up with a positive flux out. Okay, second consequence of Gauss's law plays actually back to the example that I worked earlier in which we calculated the flux out of a sphere. And basically this consequence is that the size of the Gaussian surface does not matter. Gauss's law will still hold true. Similarly, the charge distribution within the surface doesn't matter. You still will get the same flux back out of the surface. Okay, with that said, the total charge enclosed basically means take the total positive charge enclosed and subtract the total negative charge enclosed. So if we had a +1 charge here and a -1 charge here, the total charge enclosed would actually be 0. So bear that in mind. So three basic consequences, or two consequences in a rule. Only total charge matters. Doesn't matter how it's distributed. It doesn't matter how big the surface is. It in fact doesn't actually matter what shape the surface has. The flux will still in fact be the same out of it as long as the charge inside is the same. So I think it's time for another round of relatively quick examples. Okay, our first example is to determine the magnitude of the electric field created by a conducting wire of length L and charge Q. So I'm going to draw the wire. The wire is here. The wire has charge Q. It has length L. So from here to here would be L. We're going to assume it's a pretty long wire. Of course, if it's a really short wire, then it starts to look like a point charge. And what we want to know is what is the electric field strength right here at some point far away from the wire, or maybe nearby. So how are we going to do that? Well, the way to do that is that we want to create for ourselves a Gaussian surface, and that Gaussian surface should have this point on it. And that Gaussian surface I'm going to choose to be a cylinder. So this is the best I can do for drawing a cylinder. And here is the top of the cylinder. Sorry, it's not the straightest cylinder in the world. And despite my bad drawing, this wire of charge actually is passing through the center of the cylinder. So we'll say that this right here is distance r, this right here is distance r, this out here is distance r, etc. And similarly from the bottom, r, r, r. Okay, why a cylinder? Well, recall from the last set of lectures that if I wanted to draw the electric field line for this thing, it actually would basically look something like this. It's basically passing outward radially, but radially within a single plane from each point. So this one is like this. Down here, it's basically like this. And if we come down further, you get the same pattern again down here, like so. So in other words, no matter where you are in this cylinder, the electric field is locally going to be perpendicular to the lateral face of the cylinder. So E dot A just ends up being E times A. So Gauss's law says that the flux should be the enclosed charge divided by epsilon naught. So the enclosed charge in this case is whatever Q is. So call her Q or epsilon naught. is going to depend upon how much of this wire we enclose. So that could be given by lambda times L, if you'd prefer, where lambda is defined as the charge per unit length, divided by epsilon naught over here. We're looking for E. So E is going to be whatever the flux is. We'll call it Q over epsilon naught divided by A. So what is A? Well, A is the lateral area of this whole cylinder. So this looks like Q over epsilon naught times 1 over, this is for the 1 over A part. Lateral area of a cylinder is 2 times pi times radius of the cylinder times height. So E is basically looks like lambda times L over epsilon naught times 1 over 2 pi RL. Hence why I broke this up into lambda L, because we can now cancel some terms here. And so E is going to look like lambda over epsilon naught pi times R. And this is in fact an expression which you could have obtained using Coulomb's law, albeit the way that you get this from Coulomb's law is that you've got to integrate over basically the length of this wire from this point. So if you're doing a physics with no calculus class, it's going to be awful difficult to figure out what the electric field strength is without it just being told to you. But here we found it. Notice no calculus was involved here. So we found it algebraically using Gauss's law. And that's one of the great strengths of Gauss's law, is doing something like this. Here's another quick example. We have this closed surface and there are some charges in it, and we want to know what's the electric field flux through the shaded surface. Well, again, we can say that the total flux, which is E dot A, is whatever the enclosed charge is divided by epsilon naught. So this therefore is -3 coulombs plus -5 coulombs plus 2 coulombs divided by epsilon naught. And so the total flux through this surface, the total electric field flux I mean, is -5 minus 3 is -8 plus 2 is 6, -6 that is, so it would be -6 coulombs over epsilon naught. And we can in fact calculate that because again epsilon naught was 8.85 times basically 10 to the minus 12 coulombs squared Newton meters squared. So this entire thing then has a flux of, if you divide 6 by that, approximately, I guess with one significant figure, this would be basically 7 times 10 to the minus 13 Newton meters squared per coulomb squared. Coulomb, not coulomb squared. So that's the total flux outward from this surface. What I want to talk about now is free charges within a conductor. So we've already kind of said loosely that a good conductor is an object in which electric charges can freely flow around. And so the conductor has some free electrons, it has some holes, which are basically the equivalent of removing an electron from an atom. So now there's a hole in which you can put an electron. There's a charge hole. It's basically the equivalent of a positive charge. And we can transfer electrons and likewise holes from one atom to the next. But a conductor tends to go to to electrostatic equilibrium. And what that means is that there's no net force on any charge in the conductor. And similarly, it means that there's no electric field in the conductor. Because if there is a net force, then there must be an electric field to produce that net electrical force. So if there's no electrical force, there's no electrical field. And what this basically means is that all of the electrical charges that are able to move around will move around in an isolated conductor until electrostatic equilibrium is achieved. So they'll rearrange themselves around the conductor until each one has a net force of 0 upon it. What this means is that inside of the conducting material itself, when it's at equilibrium, the electric field is 0. This is true as long as you are inside the medium of the conductor. So if you have a solid metal ball, then the electric field anywhere inside of that solid conducting metal ball is 0. And thanks to Gauss's law, we know that the flux through a surface has to be the total charge enclosed divided by the permittivity. Well, if the electric field is 0 everywhere inside of an object, that means that any given surface placed inside the object will have a flux of 0 through it, which in turn implies that that surface must have, so long as it's totally enclosed, as long as the surface itself is totally enclosed in the conductor, that surface must contain no charges within it. So the implication of this is that any excess charges are going to reside at the surface or surfaces of the conductor. I say surfaces because, for example, you can have a conductor that's a solid metal ball that you've hollowed out a portion of the middle, and you might have charges residing on the outside surface, and you might have charges residing on the inside surface of this metal conductor. Finally, if there is an irregular shape to the conductor, then the charges are going to tend to accumulate in regions which have the smallest radius of curvature. That would be sharp points. So let's look at this in a little more depth. There is a non-zero electric field inside the material of a conductor if it's at equilibrium. So this diagram is sort of describing what a conductor at equilibrium might look like. Now note that there's an external electric field here. What's happened is the electrons have moved against the field lines, the protons or the holes have moved with the field lines, and the end result is that there is no electric field inside of this conductor. You get a superposition principle. You can add these external fields to what would be the created internal field if you just had a charge configuration like this and no field out here. When you add up this field plus this configuration field, you'll end up with 0 on the inside. Basically what happens is, as I just described, if you do have an electric field inside the conductor somewhere, then any negative charge can move against that field line, any positive charge can move along that field line, or be accelerated along or be accelerated against is a more proper way of saying it. And so basically you'd have accelerating charges, and if you have accelerating things, then you don't have a system at equilibrium. So by definition, a system at equilibrium has no acceleration, and therefore there are no electric fields within a conductor at equilibrium. Okay, second consequence is if you do have an excess charge in the conductor, then it's going to have to move to the conductor's surface or one of the surfaces. And one way of seeing that is, suppose that I placed a charge here in the very middle of this conductor. Well, what that would imply is that then there would be some electric field lines radiating out or radiating in to that charge, which would mean that any other charges in the vicinity would not be at equilibrium with respect to that charge. You basically can figure out that there is some net electric field because you can create a Gaussian surface around that charge. Basically, if there are any other charges or holes, then this thing is going to get repelled until it's as far away as it can be from the others, which is ultimately going to stick it somewhere on the surface. And basically the charges will then rearrange themselves on the surface so that they are uniformly distributed, provided that there's no external electric field. Any extra charge that moves inward basically creates an imbalance in the electric field, and so therefore you no longer have a conductor which is at equilibrium. The conductor, in turn, if you treat it from the outside, will act as if it is a point charge with whatever the total charge of the conductor is. The point charge will act as if it's located at the center of the conductor. So if I'm measuring the electric field out here, then this electric field will have the same strength from this conductor as it would have had if all these positive charges were just a single point in the middle of the conductor. If I go here and try to measure what the electric field strength is, I'm inside the conductor. It's got a strength of 0. The way that the electric fields work on a conductor that is, let's say, not smooth, or that has a non-uniform radius or what have you, is this. Anywhere that you have an electric field touching the surface of a conductor, it will have to ultimately be perpendicular to that surface. And the reason why that is because if you had a parallel component to the electric field on the surface, then locally any charge placed there will be free to move. Now again, remember that inside a conductor there are always charges. There are always electrons and holes. If the conductor is neutrally charged, then it means there's the same number of electrons as there are holes, but there are still electrons and holes. If you apply an electric field, then all the electrons will accelerate in the opposite direction of that field. All the holes will accelerate in the same direction as that field. And this means that the charges, the electrons and the holes, will ultimately separate in such a way that the charges rearrange until the whole electric field is perpendicular to the surface of the conductor. So at that point in time, then the conductor will be at equilibrium again. The implication of this, or maybe I should say one interesting implication of it, is that if you have a conductor that has some shape like this, where there's a relatively sharp point in one location and not so much of a sharp point elsewhere, you will tend to ultimately accumulate charges at that location, and similarly you will tend to have a much stronger electric field near that point than you have far away from that point. If you have a pointy edge, that's where the charges are going to try to accumulate, and that's where the field is going to be strongest. And that's just a consequence of the fact that the electric field lines have to be perpendicular to the surface everywhere for a conductor. And the parallel component has to be 0, or else the electrons and or holes will tend to move. Gauss's law also applies to gravity, as was said before. It's just that now we talk about gravitational field lines. The equivalent to charge is, of course, mass. If we have the Earth and there's a little spot in the middle of the Earth and we have an object sitting in the spot here, and this is hollowed out, and this is solid, 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 solid. I'm not trying to draw field lines, I'm just trying to show that all this is solid. And we want to know what's the gravitational acceleration for the object that's here. Well, recall that acceleration, or g if you want, is going to be force of gravity divided by the mass of the object. And so that would be equivalent to, well, we already kind of used the gravitational constant for big G, so I'm going to call it maybe fancy big G to represent the G field, times the mass of the object divided by the mass of the object. So this is the force, this is the mass of the object, this goes away. So we're looking for what's the total gravitational field in here. The flux for Gauss's law to gravity is basically going to be mass enclosed divided by some constant. I'll call it c. And that is going to be equal to the gravitational field flux, which is like this. Well, if you look here, if I were to draw a little sphere around this guy here in this hollow area, there is no mass actually enclosed. This is a test mass, which basically means it doesn't count into the Gauss's law. So we're only looking for what's the gravitational field experienced by the test mass, because like a test charge, it doesn't produce any fields of its own. Well, the mass enclosed is 0, so that means that the gravitational field times the area is 0. The area is not 0, and it's also hopefully clear that the field lines would basically be like this if there were any. In other words, they should be sort of perpendicular to this wall if there was actually some mass in here. There's no mass in here. There's no field lines in here. This area is empty. Basically, we can say that the gravitational field is 0, and what that means is that the gravitational acceleration at the center of the Earth is also 0. So I'm ready now to work a few longer examples to close out this lecture. We'll start here with a question that says you've got some electric field of some given strength, and it's passing through a prism which has a cross-section of an equilateral triangle, and then other sides have square cross-sections. And so we want to know what's the flux through each side in two cases. In the first case, the field lines are parallel to one of the square faces. The other case, they're perpendicular to one of the square faces. As best I can render it, this is basically the diagram of this field configuration. So it is parallel to this face that is acting as the base of the prism. Therefore, it's not going to be perpendicular to any other given face. What we need to do is perhaps label some of these faces, because the total field flux, phi sub e, is going to be the flux through each face. So we'll call the bottom face 1. This can be face 2. This can be face 3. Here's 4. And here's 5. So it's going to be 1 plus 2 plus 3 plus 4. Oops. Plus phi 5. Now, from Gauss's law, we should be able to tell immediately that the total flux is 0. So I'm going to write that in over here, but we can actually kind of show that that's true by calculating this piecemeal and then adding the 5 pieces together. In this particular case, we're going parallel to one of the square faces. It actually is also therefore parallel to both of the triangular faces. So this one and this one are actually both going to be 0. So we just calculated for 2 of the faces. So we have basically these 3 to remain. Now, since the field is parallel to face number 1, this term also needs to be 0. Because if E is parallel to A, then the flux is going to be 0. That was one of the conditions. Basically, what this would mean is cosine of theta equals 0 because theta would be 90 degrees. So what we're left with is figuring out what the angle is between the field lines in each of these faces. So here is this face. On this side we would have this face. So we're going to have, we'll call this phi 3 or theta 3, and we'll call this one theta 2. So basically what we have to do to find the flux for each face is this. Phi 2 is going to be the electric field strength times the area times the cosine of theta 2. This right here was given in the problem as 30 newtons per coulomb. This right here we get because area is equal to the length times the width of each side. So that's 4 square meters. So we basically need to find theta 2, and similarly for theta 3. The E field and the area both are equal. We just have to find what is the cosine of this angle. So what is the cosine of this angle? Let's draw this thing from the side. So here is a line that's perpendicular to the E field, and basically from the side we have this right here, this right here, and then our E field is cutting through like this. And so our perpendicular component is like this. Here is our theta 2. This triangle is equilateral, so that makes this right here a 60-degree angle. This thing is 90. This is half a 60 is 30 degrees. So this line that cuts through is going to have the same angles, 90 degrees, and this is 60 degrees. So we have 60 plus 90 plus theta 2 is 180 degrees. So 60 degrees plus 90 degrees plus theta 2 is 180 degrees, because we've gone from here, through here, through here, and now we're on the other side of this line. So therefore theta 2 is 180 minus 90 minus 60 is 30 degrees. And you can see, by the way, that if I draw the other side of this triangle, that now I have theta 3 over here, because this guy is also 60. This guy right here is also 30 degrees. And if we extend this electric field line like so, and we extend out the area like so, we have the same scenario. So this is also equal to theta 3. Okay, so what is the cosine of 30 degrees? Well, cosine of theta 3 becomes cosine of 30 degrees becomes square root of 3 over 2. And the approximate value of that is just a little less than 0.9. Specifically, it's 0.866. Okay, so the flux through each face then is as follows. We notice that it's going in through face 3 and out through face 2. So we can write phi 2 is equal to negative phi 3 is equal to 0.866 times the area, which was 4 meters squared, times the electric field strength, which was 30. And so that gives us basically 103.9, which with 3 significant figures is 104, basically Newton meters squared per Coulomb. And so now we've actually solved it. Because you can see that if these two are opposites and all the others are 0, then the total flux is also in fact 0. So we've solved case A. Now let's look at case B. Therefore, we have a setup that looks something like this. So once again, we can use that the total electric field flux is flux through 1 plus flux through 2 plus flux through 3 plus flux through 4 plus flux through 5. And again, Gauss's law says that this should be 0. So here is Gauss's law. Looking at the diagram, these are again parallel to face 4 and to face 5. Which means that they're perpendicular to the area vectors, so both of these terms are in fact 0. These terms are all non-zero. For the case of phi 1, since it's perpendicular, we have E dot A1 is going to be equal to E A1 times cosine of 0 degrees, or if we want to be a little fancier, we can say that it's actually the cosine of 180 degrees because it's going into the surface. And so this is basically negative 30 newtons per Coulomb times 4.00 meters squared. And so that's minus 120 newtons per Coulomb. Okay, so basically this minus sign is from this cosine of 180. It's fluxing inward. So now to get for phi 2 and phi 3, we're going to want to draw another of those diagrams that's sort of like a view from the side. So again, view from the side, here is our equilateral triangle. So this angle right here is 60 degrees. This angle right here is 60 degrees. And I'm going to draw this dashed line to represent the perpendicular part. So each of these is 30 degrees. Okay, so what is the electric field doing? Well, it's coming through perpendicular to the bottom and basically slicing upward like this. So here is what our electric field lines are basically doing. So let's see, we got to draw on the area vector. So the area vector right here has to be perpendicular to this. This right here would be theta 2. And then likewise, your area vector over here is perpendicular. This right here is theta 3. Okay, let's see here. 60 degrees, this right here has to be 90. This right here, therefore, is 30 degrees. So 30 plus 90 plus theta 2 is 180. So theta 2 is equal to 180 minus 90 minus 30, which is 60 degrees. And theta 3, you can see, is the same because this right here must be a 30-degree angle. So theta 3 is also 180 minus 90 minus 30. And so therefore both theta 2 and theta 3 are 60 degrees. Note that the flux is outward through both of these two faces. So we can basically write that theta that phi2, flux through 2, and flux through 3 are equal, and they are basically going to be E times A times cosine of 60 degrees, where A is the area for either A2 or A3. So this then is 30 newtons per coulomb times 4.00 meters squared, and then cosine of 60 is a half, and so phi 2 and phi 3 are equal, and they are specifically equal to 60 newtons per coulomb, and it's positive because it's fluxing outward through them. So we've solved for phi 1, phi 2, and phi 3. So let's verify Gauss's law. Phi 1 is minus 120, plus 60 is still negative 60, plus another 60 is 0. So Gauss's law is confirmed again. Okay, for our next example, what I want to look at is what basically is the electric field inside and outside of this spherical conducting shell. Spherical conducting shell means it's basically a sphere which has been hollowed out, and we're going to figure out what is the electric field given a total charge Q on the surface. And we're going to do that also for what happens if you place a charge of minus 2Q at the center of this shell. So initially there's no charge, then we'll do it again with charge at the center. The shell means that it's partially hollowed out, so there is some thickness here, but it is mostly hollow. Okay, so our first condition is that we have a shell, that's like this, and all the positive charges are ringing the outside of it. What we want to know is what is the magnitude of the electric field, let's say at this point right here, R, where R is less than this inner radius B. Okay, so the total flux has to be the charge enclosed divided by epsilon naught, and so that's 0. But the total flux should be E dot A. And so if this is 0 and we pick an arbitrary surface, A is not 0, and we cannot say that E is perpendicular to the A vector, which means tangent to this surface at any point. Therefore, it follows that the electric field value is 0 inside of this conducting shell. Now, what about outside? So outside, we end up with something like this. So here's a nicer drawing of that shell. Again, we have positive charges lining the surface of the shell. This is as best I can draw them. And of course, you can have electric field lines leaving from the shell like so. And so what we're going to do is we're going to pick an arbitrary Gaussian surface that goes outside of this shell. Maybe our Gaussian surface is like this. And this Gaussian surface has, again, a radius of r, where r is now larger than the radius of the shell. So now flux, again, is the enclosed charge divided by epsilon naught. It's not 0. And so we can say E dot A is Q enclosed, which actually is just the charge Q that's given over epsilon naught. Now what's the area of this Gaussian surface? Well, the Gaussian surface is a sphere. So the area must be the surface area of a sphere, which is 4 pi r squared, it has a radius of r. So E has to be this divided by A, so that would be Q divided by 4 pi r squared epsilon naught. And if we rearrange stuff, of course, that's the same as saying Q over r squared times 1 over 4 pi epsilon naught, which is in fact the same formula that we would use if we just had a single charge of value Q located right here at the center and no charge on the conductor. So now what happens if we have some actual charge in the center of the conductor? In fact, minus 2Q. Well, in this case, this becomes Q enclosed over epsilon naught, which is just 2Q over epsilon naught. So this becomes 2Q over epsilon naught. It's negative. And so this right here, these two lines stop applying. This one's still true, but it's uninteresting. We get basically that E is equal to minus 2Q over epsilon naught times 1 over the area, and again the area is 4 pi r squared. And so again E looks like minus 1 over 4 pi epsilon naught times 2Q over r squared. Again, that's the same form that you would have used had we had a no conductor up here. If we just only had this charge located here and we're trying to find the electric field some distance r away. Now, if we go outside of the conductor, what you end up getting is you have a total charge enclosed of Q for the conductor minus 2Q for the thing that's placed at the center. And so you end up with a total electric field of negative 1 over 4 pi epsilon naught Q over r squared, which is the equivalent field to as if you had placed minus 1 Q here at the center and had no conductor. So this brings up an interesting question. How much charge is on the inner and how much is on the outer surface of this conductor? Well, the way that we figured that out is that we know, if I can redraw this thing with maybe a slightly bigger cross-section like this, if we were to pick a Gaussian surface that is like this, that is inside of the conductor, the E field has to be 0 here in all cases. So if the E field is 0 here, if there's no charge inside, that means that this surface has plus Q charge and this has minus Q. 0 charge. Plus Q, 0. Total is plus Q. Because again, this surface could be arbitrarily large. It could be extended out to here, for example, almost touching the surface. It could have been shrunk down to here, again, almost touching this surface. And in all those cases, E is 0. And so therefore, the total charge enclosed has to be 0. So Q enclosed equals 0. What if we put minus 2Q right here? What would that do? Well, then in order to counteract this minus 2Q, if we want to have Q enclosed equals 0, this surface needs to have plus 2Q on it. Okay, well, if this surface has plus 2Q on it and the whole conductor has only plus Q, then this outer surface must have had minus q on it. So that's how we go about figuring out where the charges are located within a conductor. Alright, let's try a third example. This one is what happens if we have a sheet of charge. We've already seen what happens with a line of charge. Might as well try a sheet of charge. If we have a sheet of charge, as shown in this diagram, we basically are going to want to pick some surface that we can get the flux through easily. And as you know, everywhere the flux is going to be pointing basically away from the sheet since it's positively charged. So everywhere we're going to have a flux, a field that looks like this. And so hence the surface that we might choose is basically going to look like either a cylinder or a box. It doesn't matter too horribly much which of those two we pick, so we'll use a cylinder. So the electric field strength from Gauss's law basically is going to look like this. We'll do above the sheet and then we'll do below the sheet. Because the field is going to point in opposite directions from both. The area here and the area here are going to be equal, so we can just do for one or the other if we'd like. Basically, the total flux, E times A, should be the total enclosed charge divided by the permittivity of free space. Now it's carrying a charge of plus sigma per unit area. So Q enclosed is going to equal whatever cross-sectional area we choose, labeled A0 in this diagram, times sigma. So what that means is that the total flux, E times A becomes A0 because this is the only area that it's going to flux through. There is no flux through the lateral sides. Is basically going to look like A0 times sigma over epsilon naught. Now again, this is the total flux through both faces of both the top and the bottom of the cylinder that we've picked, or of the box that we've picked, as the case might be. So we can cancel off the A0s. This is total flux. If we just want to find the E near the top, we'd need to divide everything by 2, and so you'd end up with sigma over 2 epsilon naught. And similarly for the bottom, E bottom, you'd again get sigma over 2 times epsilon naught. And we can even, if we want, basically we could find what is the component, the z component of this field above and below the plane. If we were specific, this one is actually negative, and this one would be positive because this one's pointing down, this one's pointing up. Since we have some numbers up here, we can now plug them in. Basically, we want to know from 2 meters away. Notice that R doesn't appear anywhere in this, so this is basically irrelevant. What we have then is, what is the charge density going to be? And it's 1 millicoulomb per square meter. So the E field strength, we're 2 meters away, means we are using one of these guys. That's 1 times 10 to the minus 3 coulomb per meter squared, divided by 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Okay, so this right here gives us a total electric field strength of about 1.13 times 10 to the 8th newtons per coulomb. So that's what the electric field strength is outside of this sheet of charge. So let's look at one more example. This one will utilize a little bit of calculus to solve. Basically what has happened is we've placed a charge Q in the center of some cone, and the cone is such that the height is twice the radius of the base. And so what we want to know is what's the electric field flux through the walls of this cone. All right, so getting the flux through the walls of the cone directly is going to be a bit tricky. And so here's kind of another interesting use of Gauss's law, if you will, which is that compared to finding the flux through the walls, finding the flux through the base of the cone is going to be relatively easy. And basically what we can say is that the total electric field flux is still Q enclosed over epsilon naught. So that's going to be Q over epsilon naught. And that's basically going to be flux of the electric field through the base plus flux of the electric field through the walls. So basically, in order to find the flux of the electric field through the walls, we take Q divided by epsilon naught, both given or constant quantities, and we subtract from that the flux of the electric field through the base. So our real task here is not directly to try and compute this number or find an expression for this term, but to solve for this term, and then once we've done that, we have the answer for this term. So how do we get the flux of the electric field through the base? Well, let's draw ourselves a fresh diagram. All right, what we're ultimately looking for here is the flux of this electric field, which I've drawn some basic lines for, through this bottom surface. So the field is coming from a single point particle of charge Q and is going to be basically radial from Q. So basically what we need to do is find a way to integrate E dot dA for this circular surface. So we're finding the area of this circle dotted with the electric field value. So I'm going to have a second diagram here which kind of illustrates that a little bit. So in actuality, our dA might be some little slice like this, which we might be tempted to call a dy times a dx. In actuality, though, there is some symmetry to this problem in that it doesn't matter where in this particular direction around the circle we go, the E dot dA will be the same. It's only as we move radially along the circle this way, or in other words, as we increase this angle theta, that we get a different angle between E and dA. And in fact, this angle theta and this angle theta between E and dA are going to be the same. Okay, so what we're looking for here, we're basically trying to do an integral E dot dA through this circle on the bottom. And what that basically is going to be is E dot, our dA term basically looks like a little r d theta here. Sorry, an r dr d theta. However, because I'm already using an r here and a little r here, I'm going to choose y to represent our sort of radial distance along this plane. So dA becomes y dy times d phi, where phi is this angle in this plane right here. So this right here would represent angle phi. Now, as I said before, as we move around this circle, E dot dA is not changing. So anywhere within this ring, E dot dA is the same, and therefore part of this integral is going to become very easy. So this is basically E dot y dy d phi, call it a hat for lack of a better term. In fact, if this is y and this is the xy plane, then a hat may in fact be, say, z hat. In any case, E itself is not a function of phi. E, if we were to find the electric field value at some arbitrary point, distance little r away, is going to be 1 over 4 pi epsilon naught times q over r squared. That's a simple calculation that we can just use Coulomb's law and the definition for a electric field to get. So since there's no phi in this equation, that means that this entire integral is going to reduce to integral of basically 1 over 4 pi epsilon naught times q over r squared y dy times integral over d phi. And then maybe I should have a like a e hat vector. So basically r hat dot z hat or a hat. R hat is because the vector is along this radial direction. Z hat is because the area vector for this circle is in the z direction. So what are our limits of integration for the d phi? Well, we're maybe integrating from 0 all the way around the circle. So that's from 0 to 2 pi. So this thing right here has a value of just 2 pi. So at this point, our flux of the E field, all this is to find the flux of the E field through the base. So the flux of the E field through the base can be expressed by this integral 1 over, since I got a 2 pi here and a 4 pi here, might as well just eliminate those. 1 over 2 epsilon naught. We'll put the q over this since it's also constant. And basically y over r squared r hat dot z hat dy. So we got to do something with all of these terms right here, this mess of terms right here. And what we're going to do with this mess of terms right here is we're going to do a few little conversions. First of all, we basically want to get r and y and z, r dot z, to be in common terms. Now r dot z, this term right here, is basically, since these are both the unit vectors, by definition this has to be the cosine of whatever angle is between this vector and the z vector. Well, that angle, the angle between dA and E, is theta. So this right here is actually cosine theta. So we have a y, we have a theta, and we have an r. And if you look at this diagram, you can see that as y changes, theta changes, and r changes as well. So we need to have all three of these terms expressed as a common term. So we can have like y over y times dy. We can have theta over theta times d theta. We can have r over r times dr. We just don't want y over r times cosine theta dy. Okay, so looking at this, what I see is as follows. This right here is also the y vector. So we have a right triangle. Here's the right angle in question with big R, little r, and y. So I notice, therefore, that I can re-express some of these terms as follows. Y is big R times tangent of theta. So tangent of theta would have been y over big R. It's okay to express stuff in terms of big R because big R is a constant. Okay, so now we can get rid of the y's. However, we also need to do something about dy. So dy by d theta is basically going to look like r times, we'll just put it in terms of cosine, r over cosine squared of theta. Okay, so that means that therefore dy is equal to r over cosine squared of theta d theta. Okay, so we've dealt with this term, we've dealt with this term's already in theta, we need to convert the r squared term. We're looking over here, and again, we want to express r in terms of theta and big R, little r in terms of theta and big R. So little r is the hypotenuse, big R is the adjacent, so basically cosine of theta is big R over little r. So that's the same as saying that little r is big R divided by cosine of theta. Okay, so we'll move this stuff up out of the way a little bit, and basically we need to put all this stuff into this equation. So now we have that the flux phi EB through this bottom surface, this base, is, if we pull out a couple constants, so q over 2 epsilon naught, and we're going to do an integral. What are the limits of integration before I stick everything in? Well, we're integrating from 0 to big R, but we need to be integrating over theta. So I notice that when we're out here at big R, you would have basically a triangle that looks like this. Big R, and here's theta. This is actually a right triangle, so that means that the limits of integration are actually from 0 to 45 degrees. 45 degrees needs to be in radians, so that is pi over 4. Okay, so that's the limits of integration. Now let's do some substitutions here. So we have a y, so that is an r tangent theta. We have a cosine of theta from the dot product term. We have a dy, so that is an r over cosine squared theta times d theta term. So there's our dy. Now we're going to divide all of that by a little r squared. So little r was this, so this is r divided by cosine of theta quantity squared. So I can see that there's going to be a little bit of cancellation of terms here. So let's see, there's an r, so that's r squared, there's an r down there. So the r's drop out. I guess that's nice. There's a cosine squared theta term here, there's a cosine squared theta here. Both of these are denominators within their respective numerator and denominator, so this and this cancel. I have a tangent theta, which, as you know, is sine of theta over cosine of theta, and so this cosine and this cosine can also cancel. And so what we're left with is q over 2 epsilon naught times the integral from 0 to pi over 4. And with all this cancellation Actually, what's left over is sine of theta times d theta. And let's make sure that we've got all of our everything straightened away. This looks good. So we're going to integrate from 0 to pi over 4. Since this is sine of theta, the integral is going to leave us with a negative cosine of theta. So we have phi times phi of EB is q over 2 epsilon naught times negative cosine theta, and we're evaluating from theta equals 0 to theta equals pi over 4. Okay, so when theta is pi over 4, cosine of theta is square root 2 over 2. When theta is 0, cosine of theta is 1. Since it's a negative, this all is going to basically look like q over 2 epsilon naught times 1 minus 1 over square root 2. Yes, this looks correct. Okay, so now we found the flux through the base of this cone. Now, recall that the goal was in fact to find the flux through the sides of the cone. So therefore what we have is that theta E through the sides of the cone, or the wall of the cone, whatever you want to call it, is the total flux minus the flux from the base. And that is going to be, total flux is charge enclosed over epsilon naught. So it's that minus q over 2 epsilon naught times 1 minus 1 over square root of 2. So what does this give us? This gives us that the total flux is, I notice that this right here can be rewritten as q over 2 epsilon naught. So we're basically saying minus q over 2 root 2 epsilon naught. So this minus this term is going to leave me a q over 2 epsilon naught term, and then minus a negative means we get to add an additional q over 2 root 2 epsilon naught term. So I guess that gives us q over 2 epsilon naught times 1 plus 1 over square root 2. Alright, so that gives us the total flux through the walls of the cone. So that actually brings me to the end of this lecture. Not only of this part of the lecture, but in fact of this entire lecture set. So now you have been introduced to the concepts of charge, of electric field lines, of Coulomb's law, and now today of Gauss's law and how it can be used to compute things like the electric field strength at a given point given a charge configuration. So I hope that you have found today's video helpful, and I think it's been one of my longer videos, so I guess you have quite a bit to watch and to review, but hopefully you're able to digest a good fraction of this video. Hopefully you found this very helpful, and thanks for watching.